So first we look at double angular formula. Double angular formula, that is what is the value of sine of 2x cos 2x and tan 2x. Oh no, before that let's just derive for the sake of deriving the cot formula, that is cot of a plus b. You'll find that you don't actually have to use the cot or the cosec formula as often, but just for the sake of deriving it, I'll derive cot of a plus b over here, and you can try deriving sec and cosec formulas if you wish to. So this is nothing but 1 by tan of a plus b, and this value is actually equal to 1 minus tan a tan b, because it's actually tan a plus tan b over 1 minus tan a over tan b, but we're taking the reciprocal over here, so this is 1 minus tan a tan b by tan a tan b. But remember, we actually want the formula in terms of the cot of the individual angles, so cotangent of the individual angles, so that's what we'll try and do over here. And we know that cot theta is actually equal to 1 by tan theta, so we can actually write this as 1 minus 1 by cot a cot b, and this is also equal to cot a, hold on, 1 by cot a, that is 1 by cot a plus 1 by cot b. Now what you can do is you can take the LCM and then you can simplify that. So what actually happens is when you take cot a cot b over here and then you take the common LCM and you also take the common LCM over here, the cot a cot b actually get cut, so I'm not going to write that step. I'll just write this as cot a cot b minus 1 by cot a plus cot b, and this is the cot a plus b formula. You can also derive the cot a minus b similarly. Alright, so this is that, and now we'll move on to the double angle formula, that is sine 2x cos 2x tan 2x. We'll just derive for these. So for sine 2x, the strategy that we'll actually use is writing it in terms of sine of x plus x. Alright, so that actually turns out to it being sine x cos x, because it's actually sine a cos b plus cos a sine b, so we can actually write this as sine x into cos x plus sine x into cos x. So it turns out sine 2x is actually equal to 2 sine x cos x, and now this again is also a very important identity which will be used almost everywhere. It's even useful while integrating functions. So there's another form for this identity in terms of tangents, which are that is tan x, which is what I'll be writing over here. Now we know that sin square theta plus cos square theta is equal to 1. So in over here, what you're actually going to write is you're going to divide this expression over here by sin square x plus cos square x, and that is okay because the value of that is just 1. So we don't have to multiply divided by anything else. It's equivalent to just like dividing by 1 and then substituting it for sin square x plus cos square x. So that's what I'll be writing over here. And over here, we can actually divide this whole thing by cos square x, that is both the numerator and both the denominator. So when we do that, we can actually write 2 sin x by cos x, because I've cut the cos x, and we can also write sin square x by cos square x plus 1. Alright, so this is nothing but sin x by cos x is nothing but tan x, so we can actually write this as 2 tan x by 1 plus tan square x. And this is yet another form that is used commonly, and in fact you'll actually see this appear in inverse trigonometry quite often. So next is cos 2x, which is nothing, again we're going to write this as cos x plus cos of x plus x. So there are actually many forms of this identity, and which actually makes it pretty important. So we're going to look at each of them. So this is actually cos a cos b minus sin a sin b, right? So we can actually write this as cos x into cos x minus sin x into sin x. Alright, so this is actually equal to cos square x minus sin square x, And so this is the default form of this identity if you prefer, but there are actually many different forms of it, and this is what you'll be looking at right now. So we know that sin square theta plus cos square theta is equal to 1, right? So we can actually write cos square x over here as 1 minus sin square x. Suppose if I write this as 1 minus sin square x, and then we also have to subtract sin square x from over here. So this will actually turn out to be 1 minus 2 sin square x. And similarly, you can do the same thing for this over here. You can actually write this as 1 minus cos square x. So this is also actually equal to 2 cos square x plus 1. Nope, it's not equal plus 1, it's I believe minus 1, yeah, it's minus 1. And there's yet another identity that is derived using the same thing principle over here. That is, we derive the whole thing by cos square x. I mean sin square x plus cos square x. And so we can write this as cos square x minus sin square x by cos square x plus sin square x. Now when you do the whole procedure that you just did over here, and like by dividing it by cos square x, we actually find that this is equal to 1 minus tan square x by 1 plus tan square x. Now you might be thinking, why did I choose to divide specifically with cos square x? I could have also divided by sin square x. And that's true, because then I would have gotten a formula in terms of cot square x. I would have gotten cot square x minus 1, and this would have been cot square x plus 1. But the thing is, cot and the other sec and cosec functions are not commonly used in trigonometry, and we generally prefer to work in terms of sine, cos, and tan. And in fact, even whenever I see a problem in terms of cot x or cosec x, sec x, my first instinct is actually to change the functions to their other values, that is sine, cos, and tan. So this is the way things usually are in trigonometry. So that's why I chose to divide it with cos square x. Alright, so after that, but before I move on to the next one, I want to stress the importance of this identity and this identity over here, because this is something I will be seeing frequently. And this is also important because when you're performing integration, there is no definite formula for the integrals of sin square x and cos square x, because there are no elementary functions for which the derivatives you get as cos square x or sin square x. So what we actually do is we apply this half angle formula over here, and then we can change this in terms of the cosine and sine values of that which don't include the squares, because we could write this cos square x over here as suppose 1 plus cos 2x by 2, and we do know what the derivative of say dx is and cos 2x dx is. That is just sine 2x by 2. So using this formula we can actually find the integrals of these two functions. So this is actually a pretty useful thing when performing integration. Now the next formula over here is tan 2x, and we're going to use the same tactic, and we can actually write this as tan x plus tan x by 1 minus tan square x. So this will actually just turn out to be 2 tan x by 1 minus tan square x. And see if you can try and find alternate forms of this identity in terms of other functions. Right? So this was the double angle formulae derivation. Now there are also formulae for triple angle, but I am not going to derive them. They use the exact same principle, that is, you have to find sine of 2x plus x, and then you'll use the value for sine 2x that you found over here. So instead I'm just going to state them over here, and we can try them in your free time. So think of it as an exercise, I guess. So this is actually just equal to, hold on here, this is equal to 3 sine x minus 4 sine cube x, and cos 3x is equal to 4 cos cube x minus 3 cos x, and tan 3x I believe is 3 tan x minus tan cube x. And of course, if you feel at any point that I'm rushing, take your time through this. I mean, or normally in a class a teacher would be going with this at very slow pace, but I'm sort of rushing through it because you have the liberty to pause it at any time and then just go through it. So this is 1 minus 3 tan square x, I believe. I think so. Tan 3x. Okay, so this was the triple angle formula. Now there is yet another set of formulae that are commonly used. That is the formulae that you get when you suppose you add sine x plus sine y. I mean, sure, there's nothing wrong in just leaving it as like this, but but converting them to another form can prove useful when you want that form more desirable, and that form is something that we'll actually be looking at right now. So let's try and get those volume. Alright, so this value over here is actually equal to 2 sine of x plus y by 2 into cos of x minus y by 2. Now, to derive this, I'll actually take two angles. I'm going to express x in terms of, say, theta plus phi, arbitrary angles theta plus phi, and y in terms of theta minus phi. Alright, so when I do that, I can actually write sine of theta plus phi plus sine of theta minus phi. And now I'm going to expand this over here. I'm going to write this as sine theta cos phi plus cos theta sin phi plus sin theta cos phi and minus cos theta sin phi. So we see that these two things over here get cut, right? So we can just cut both of these, and then we can write this as sin theta cos phi. And if you actually solve for theta and phi by eliminating, and if you find it for, let's just solve it anyway. So suppose if I add these equations over here, you'll find that x plus y is actually equal to theta, x plus y, that is equal to 2 theta, and x minus y is equal to 2 phi. So you can actually say theta is equal to x plus y by 2, and x minus y is actually equal to phi is actually equal to x minus y by 2. And so you see why we made the substitution, because then we can easily express this in terms of 2 sine of x plus y by 2 into cos of x minus y by 2. So you actually see why we wish to do this, because we just gotten what we were after, because this was the expression that we needed. Because if we didn't actually express this in terms of theta plus phi and theta minus phi, there was no way to further expand these terms, and then we couldn't get this form. Now similarly, if you actually subtract this, I'm not going to do the whole thing again, I'm just going to write this as sin x minus sin y. If you actually subtract this, instead of this term getting cut, it will be this term that gets cut. So we can actually write this as 2 cos of x plus y by 2 into sine of x minus y by 2. So it's just the same thing, but the arguments have been reversed. Instead of this argument coming in the cos function, it has come in the sine function over here, and vice versa. So now we can also write something for cos of x plus y, cos x plus cos y. Again, you can do the substitution of cos of the theta plus phi and cos of theta minus phi. And what you'll get in this case is actually 2 cos x plus y by 2 into cos of x minus y by 2, because the other things get cut. The sine, that is a 2 sine x, 2 sine theta sine phi, the sine theta sine phi terms will actually get cut in the case of the cos formula. Again, you can also do it for cos x minus cos y. And I actually prefer writing this the other way, that is cos y minus cos x, and that is actually because when you write it this way, there's a negative sign. We'll actually write this as 2 sine x plus y by 2 into sine x minus y by 2. So to get rid of the negative sign, I usually write this as cos y minus cos x. So these are what you would normally call the transformation formulae, that is to convert from a sum to a product and vice versa. And that is vice versa because you can always write this as 2 sine theta 2 sine phi, and 2 sine theta sine phi, and then this would actually be sine theta. I mean, sorry, I was talking about over here. That is, you could always write this as what I'm saying is you can always write this as 2 sine theta cos phi, and then this would actually be sine of theta plus phi plus sine of theta plus phi. So if you wanted to convert from product to sum, you could also do that. That's what I was trying to say. I'm sorry if it became a bit confusing over there. So that is pretty much it, I think. But before leaving you, I did say that I would give a few sort of exercises, I guess, as homework. So, as homework, you could try and prove these three identities. These also turn up fairly often. Not fairly often, but think that they are also pretty useful. So the first one is a sine of a plus b into sine of a minus b is equal to sine squared a minus sine squared b. Alright, now the second identity is sine of a into sine of pi by 3 minus a into sine of pi by 3 plus a is equal to 1 by 4 sine 3a. And the last one is tan 3x into tan 2x into tan x is equal to tan 3x minus tan 2x minus x. So there's that, and thank you for watching, and I believe the next video or videos is going to be sort of a mini series on fluids. That I'll be talking about Pascal's law, equation of continuity, Bernoulli's theorem, and the applications of Bernoulli's theorem. So keep an eye out for that, I guess. Thank you for watching. I'm sorry, this is actually a tan x. Yeah.